Out there in the vast emptiness between the stars, hidden within swirling clouds of cosmic dust and gas, something strange is happening. These interstellar giants, mysterious, beautiful, and ever-changing, are whispering secrets we don't yet understand. Imagine a signal cutting through the darkness of space, a pulse of energy so unusual that even the sharpest scientific minds can't explain it. No, this isn't science fiction. This is real. Somewhere in the depths of these glowing gas clouds, signals are being sent, or perhaps just leaking out, that challenge everything we think we know about the universe. For decades, astronomers have trained their telescopes on these celestial enigmas, hoping to decode the messages hidden within their flickering light. But the more we listen, the more questions arise. Why do these signals appear so unpredictably? What could possibly generate such bizarre patterns of energy? And most tantalizing of all, could they be something more than just cosmic static? The truth is, each unexplained pulse from these interstellar clouds is like a piece of a puzzle we're only beginning to assemble. Some might be caused by exotic physics we haven't discovered yet. Others could hint at processes so alien to our understanding that they rewrite the rules of astrophysics itself. Today, we're diving into 25 of the most baffling signals ever detected from these cosmic labyrinths. Some flicker like distant lighthouses only to vanish without a trace. Others repeat in rhythms that defy natural explanation. A few even seem to carry patterns that tease the edges of intelligibility, enough to make you wonder if we're truly alone in the universe. This journey isn't just about cataloging anomalies, it's about peering into the unknown and asking the biggest questions of all: what's really out there? And what might these cosmic whispers be trying to tell us? Strap in, because by the end of this, you'll never look at the night sky the same way again. One of the most famous cosmic mysteries began on a quiet August night in 1977, when a radio telescope in Ohio picked up something extraordinary. A narrowband signal blazing at a frequency scientists had long considered a potential marker of extraterrestrial communication erupted from the depths of space, so powerful that astronomer Jerry Amon scrawled, "Wow," in red ink on the printout. For 72 seconds, it screamed across the cosmos before vanishing, never to repeat. Decades later, the wow signal remains a haunting enigma, a fleeting burst of energy that defies all attempts at explanation. What makes this signal so intriguing is not just its strength, but its origin. It came from the direction of Sagittarius, a region dense with interstellar gas clouds, those vast, turbulent nurseries where stars are born. While many dismissed it as a random cosmic blip, others wondered, could these clouds be hiding something more? Some theories suggest natural phenomena, like amplified emissions from hydrogen swirling within the clouds. But then, why hasn't it happened again? Other possibilities push the boundaries of imagination. Could the signal have been a brief, unintentional beacon from a distant civilization, or even some form of cosmic interference we don't yet understand? The real frustration lies in the silence that followed. Despite countless searches, no telescope has ever detected another signal like it. It's as if the universe teased us with a single, cryptic message and then refused to say more. And that's the enduring allure of the wow signal. It's not just a mystery, it's a challenge, a dare to keep listening, to keep questioning, because somewhere in those interstellar clouds, the answer might still be waiting. Decades after that Ohio telescope first caught the wow signal, scientists armed with far more powerful tools have turned their gaze back to that same patch of sky. Modern radio telescopes like the Very Large Array and the Allen Telescope Array, designed to pick up even the faintest cosmic whispers, have combed the region for any trace of a repeat signal. Yet silence persists. What makes this mystery deepen is how technology has evolved since 1977. Back then, astronomers relied on single-dish telescopes that could only observe one point in the sky at a time. Today's arrays can scan vast swaths of space simultaneously, filtering out interference from satellites and earthly noise with precision. If the WOW signal were a natural phenomenon, why hasn't it shown up again under far more sensitive scrutiny? One compelling theory suggests the signal might have been a brief but extreme amplification of background noise, a cosmic fluke caused by interstellar gas acting like a lens, focusing distant radio waves into a fleeting spike. Gas clouds, after all, are chaotic environments where turbulence and magnetic fields can create unpredictable effects. But critics point out that such an event would require incredibly specific conditions, almost too perfect to occur just once in 40+ years. Other researchers propose more exotic explanations, like the disintegration of a comet's hydrogen cloud, except no known comet was passing through that region at the time. The more we learn, the more the WOW signal seems to resist easy categorization. Perhaps the most tantalizing modern twist comes from the field of astrobiology. Recent studies of nearby exoplanets reveal that the WOW signal originated near a star strikingly similar to our Sun, one that could theoretically host habitable worlds. While this doesn't prove an intelligent source, it adds a layer of intrigue to the puzzle. Imagine if, just for 72 seconds, something or someone transmitted a signal powerful enough to cross the cosmos, only to fall silent forever. Whether natural or not, the WOW signal remains a beacon of possibility, reminding us that the universe still holds secrets we've only begun to glimpse. And until we catch it again or find something like it, that red-inked WOW on an old printout will keep challenging us to look deeper. If the WOW signal was a fleeting cosmic shout, then the Lorimer Burst was more like a scream, one that echoed across the universe before disappearing without a trace. Discovered in 2007 by astronomer Duncan Lorimer while combing through old data from Australia's Parkes radio telescope, this burst of radio waves lasted just 5 milliseconds but packed more energy than our Sun emits in a month. What set it apart wasn't just its raw power, but the way it seemed to come from somewhere beyond our galaxy, tearing through the fabric of space with a signature so bizarre it left scientists questioning whether they'd witnessed a natural event or something far stranger. The Lorimer Burst's origins trace back to a region near the Small Magellanic Cloud, a satellite galaxy of the Milky Way enveloped in sprawling interstellar gas clouds. These clouds, typically seen as cosmic way stations for star formation, might have played a crucial role in the burst's journey. As the signal traveled through this dense, magnetized gas, it became dispersed. Its longer wavelength slowed slightly compared to the shorter ones, a fingerprint that helped astronomers estimate its mind-boggling distance. Yet here's the puzzle. If such bursts were common, why had no one detected them before? And why has this particular one never repeated? One leading theory suggests the burst could have been caused by the catastrophic death of a neutron star, a magnetar collapsing into a black hole, releasing a final, explosive pulse. The gas clouds along its path might have acted like a funhouse mirror, distorting and amplifying the signal before it reached us. But skeptics point out that such an event should leave behind detectable remnants, like X-ray afterglows or gravitational waves, neither of which were found. Another possibility involves ancient stellar collisions, where two superdense objects merge in a flash of energy. Yet even these events should recur in some form, making the Lorimer Burst's one-and-done nature all the more perplexing. What truly captivates researchers is how this burst defies expectations. Unlike later fast radio bursts, which sometimes repeat or arrive in predictable patterns, the Lorimer Burst stands alone, a solitary anomaly with no obvious explanation. Some have even speculated about artificial origins, though most dismiss this as unlikely given the sheer energy required. But perhaps the most tantalizing clue lies in the gas clouds themselves. These turbulent regions, filled with charged particles and magnetic fields, might be capable of generating or modifying signals in ways we don't yet understand. Could they be hiding other bursts distorted beyond recognition? Or might they occasionally focus energy like a cosmic magnifying glass, creating brief, brilliant flashes visible across the universe? For now, the Lorimer Burst remains a cosmic ghost, a fleeting signal that rewrote the rules of radio astronomy before vanishing into the void. Its legacy, though, is undeniable. It sparked an entire field of study, inspiring astronomers to scan the skies for similar bursts and leading to the discovery of hundreds more. Yet none have matched its raw intensity or its air of mystery. In the end, it's a reminder that the universe still holds phenomena so strange, so fleeting, that they leave us with more questions than answers. And somewhere in those swirling gas clouds, the next great cosmic puzzle might already be waiting. Fast radio bursts have become one of the most electrifying puzzles in modern astronomy, and their potential link to interstellar gas clouds only deepens the intrigue. These ultra-brief cosmic flashes, some unleashing as much energy in milliseconds as our Sun does in days, seem to favor regions rich in turbulent gas, raising the question: are these clouds the source, the messenger, or something far more unexpected? One camp of researchers argues that magnetars, highly magnetized neutron stars, could be the culprits. Picture a spinning stellar corpse, its magnetic field so intense it occasionally snaps like an over-twisted rubber band, releasing a devastating blast of radio waves. Gas clouds near these magnetars might then act as cosmic amplifiers, their charged particles twisting and focusing the signal into the ultra-sharp spikes we detect. Supporting this, astronomers in 2020 discovered an FRB originating from a known magnetar within our own galaxy. But here's the catch: most FRBs come from vastly farther away, and their signatures often show patterns that don't quite fit the magnetar mold. Then there's the black hole angle. Some theorists propose that when supermassive black holes at galaxy centers devour stars or merge with one another, the resulting chaos could generate shockwaves that ripple through surrounding gas clouds, briefly turning them into colossal radio transmitters. It's a compelling idea, except many FRBs appear in quieter galactic neighborhoods far from these gravitational monsters. Even stranger are the rare repeating bursts which defy the single catastrophe explanation entirely. Of course, no discussion of FRBs would be complete without acknowledging the elephant in the cosmos. Could some of these signals be artificial? The idea isn't as far-fetched as it sounds. A civilization capable of harnessing stellar-scale energy might use directed radio pulses for communication or even propulsion, as some have suggested. The gas clouds along the signal's path could scatter and distort these transmissions, explaining why they sometimes appear so fragmented. But before you leap to conclusions, consider the sheer energy required. The average FRB releases as much power as hundreds of millions of suns in a blink. If these were beacons, they'd dwarf anything humanity could muster. Perhaps the most fascinating twist comes from recent observations showing how gas clouds might leave their fingerprints on these signals. As FRBs traverse these turbulent regions, their wavelengths stretch and compress like a symphony passing through a hall of mirrors, each distortion revealing secrets about the cloud's density and magnetic fields. In this light, FRBs aren't just mysteries, they're tools. By studying how the signals change, astronomers can map the invisible architecture of the universe, probing gas clouds billions of light years away as though they were holding them up to a cosmic light bulb. What emerges is a paradox. The more we learn about FRBs, the more they resist simple explanations. They could be the death cries of stars, the birth pangs of black holes, or even the static of an unimaginably vast cosmic engine we've yet to comprehend. But one truth remains undeniable wherever these bursts come from: the interstellar gas clouds they pass through aren't just bystanders. They're active players in the drama, shaping, amplifying, and sometimes obscuring the signals in ways we're only beginning to decode. And with every new FRB detected, the story grows richer, leaving us to wonder what other secrets these glowing nebulous giants might be hiding. In 2020, astronomers with the Breakthrough Listen project detected something that sent shockwaves through the scientific community, a narrowband radio signal clocking in at 982 MHz, emanating from the direction of Proxima Centauri, the closest star system to our own. Dubbed BLC-1, this signal appeared to tick all the boxes for potential artificial origin. It was concentrated in a tight frequency range, drifted in a way consistent with a transmitter on a moving planet, and originated from a system known to host an Earth-sized world within the habitable zone. For a brief, electrifying moment, the possibility of contact seemed tantalizingly close. But as with all great cosmic mysteries, the truth proved far more complicated, and interstellar gas clouds might hold the key to unraveling it. The initial excitement gave way to rigorous scrutiny. Unlike the wow signal or Lorimer Burst, BLC-1 wasn't a one-off event. It reappeared sporadically over several observations, yet never in a predictable pattern. This inconsistency raised eyebrows. If this was an intentional transmission, why the irregularity? One compelling answer lies in the turbulent soup of gas and dust drifting between stars. The space between Proxima Centauri and Earth isn't empty. It's threaded with diffuse interstellar clouds that can distort, refract, or even amplify radio waves passing through them. Like a message shouted across a windy canyon, BLC-1's signal might have been twisted by these clouds, creating the illusion of artificial structure when it was just cosmic interference playing tricks on our instruments. Skeptics pointed to another clue: the signal's frequency overlapped with known human-made radio interference. Ground-based transmitters, satellites, or even poorly shielded electronics could mimic an extraterrestrial signal. But here's where gas clouds add another layer of intrigue. If earthly interference was the culprit, why did the signal only appear when telescopes were pointed at Proxima Centauri? Some researchers speculate that interstellar plasma-charged gas permeating space might have reflected or refracted human-made radio noise, redirecting it precisely along the line of sight to the star. It's as if the universe conspired to create the perfect cosmic mirage. The debate took another turn when astronomers analyzed Proxima Centauri's environment more closely. The star is a red dwarf prone to violent flares that bathe its planets in radiation. Could BLC-1 have been a natural byproduct of such stellar activity? Gas clouds within the system itself might have acted as resonators, converting flares into coherent radio bursts that, by sheer chance, resembled artificial signals. This explanation gained traction when follow-up observations failed to detect repeats under controlled conditions. Yet even this theory doesn't fully resolve the mystery. The signal's frequency drift, a hallmark of a transmitter on a moving planet, remains oddly precise for a random astrophysical event. What makes BLC-1 so uniquely frustrating is its almost quality. It wasn't clearly natural, nor was it definitively artificial. Instead, it lingered in the gray zone, challenging astronomers to reconsider how gas clouds and other interstellar phenomena might mimic or mask signals of intelligent origin. The controversy also highlighted a deeper truth. As our search for extraterrestrial intelligence grows more sophisticated, so too must our understanding of the cosmic mediums through which signals travel. Gas clouds aren't just passive backdrops, they're dynamic filters capable of distorting, amplifying, or even creating signals that fool even the most advanced detectors. In the end, BLC-1 faded into the archives as an unsolved anomaly, a reminder that the universe delights in keeping us guessing. Whether it was a technical glitch, a quirk of interstellar physics, or something more profound, the signal's legacy endures. It taught us that the road to discovery is paved with false alarms and cosmic red herrings, each one sharpening our tools and tempering our expectations. And as we continue listening to the stars, one thing is certain: the next signal might be the real thing, or it might be another cosmic echo whispering through the gas-cloaked void. The discovery of BLC-1 didn't just spark debate. It forced a reckoning in the search for extraterrestrial intelligence. For decades, SETI researchers had operated on a simple assumption: narrowband radio signals, especially those drifting in frequency as a transmitter on a planet would, were the gold standard for detecting alien civilizations. BLC-1 fit that profile perfectly until it didn't. Its irregular reappearances, combined with the unsettling overlap with human-made interference, exposed a vulnerability in the search. Suddenly, the cosmos felt less like a quiet desert where artificial signals would stand out and more like a crowded marketplace, buzzing with natural and human-generated noise. Interstellar gas clouds, once considered mere static in the background, emerged as potential puppeteers, capable of twisting ordinary signals into something that looked eerily intentional. This realization sent shockwaves through the SETI community. If gas clouds could distort or amplify natural phenomena, or even human-made transmissions into false positives, how could astronomers ever be certain they'd found the real thing? The answer lay in developing new filters, not just for earthly interference but for the cosmic kind. Researchers began modeling how signals might change as they passed through turbulent interstellar gas, simulating how a transmission from Proxima Centauri could warp en route to Earth. These models revealed something startling. Under the right conditions, gas clouds could act like cosmic prisms, splitting a single natural burst into multiple signals that mimicked artificial repetition. Suddenly, the rules for identifying alien transmissions needed rewriting, but the impact of BLC-1 went deeper than technical adjustments. It challenged the philosophical foundations of SETI. For years, the field had leaned on the Drake equation, a framework estimating the number of detectable civilizations based on factors like star formation and planetary habitability. Now there was an unspoken variable: the interstellar medium itself. Gas clouds, long ignored as passive backdrops, became active players in the equation. Their density, magnetic fields, and even their motion could determine whether a signal reached us intact, distorted beyond recognition, or not at all. This added a layer of cosmic uncertainty, suggesting that even if intelligent life were broadcasting, their messages might be scrambled by the very fabric of space before we could hear them. Yet BLC-1's legacy isn't just about obstacles, it's also about opportunities. The signal's ambiguity spurred innovations in signal verification. Projects like Breakthrough Listen now employ machine learning to distinguish between artificial patterns and natural astrophysical noise, training algorithms on vast datasets that include gas cloud interactions. Meanwhile, radio telescopes have begun monitoring signals across wider frequency ranges, recognizing that interstellar gas can shift a transmission's wavelength unpredictably. These advances didn't just make SETI more rigorous, they transformed it into a multidisciplinary effort blending astrophysics, data science, and even plasma physics to decode the universe's whispers. Perhaps the most profound lesson of BLC-1 is humility. It reminded us that the universe is far messier and more dynamic than our cleanest models predict. Gas clouds aren't just cosmic fog, they're living, shifting entities that can hide, alter, or even Chinese letter signals in ways we're only beginning to grasp. As we continue listening to the stars, we're no longer just searching for aliens, we're learning to read the universe's fine print, one distorted, enigmatic signal at a time. And in that complexity lies a thrilling possibility. The next great detection might not come from a clear, repeating beacon, but from something subtler, hiding in the noise, waiting for us to untangle its secrets. Among the countless fast radio bursts discovered so far, one stands out not for its power or distance, but for its stubborn refusal to stay silent. Known as FRB 201809116, this repeating burst, detected by Canada's CHIME telescope, shattered expectations by firing off signals in a rhythmic pattern unlike anything seen before. Unlike the single, catastrophic blasts of most FRBs, This one pulsed at intervals that defied easy explanation, sometimes quiet for months, then suddenly erupting in clusters of activity. What made it even more intriguing was how these bursts seemed to dance through the interstellar medium, their signals subtly altered by the very gas clouds they passed through. Here was a cosmic broadcast that didn't just flash and fade, but lingered, teasing astronomers with clues about the universe's hidden wiring. The CHIME repeater's bursts carried a peculiar fingerprint. Their wavelengths were stretched and twisted in ways that pointed directly to the influence of magnetized gas clouds along their path. Imagine shouting into a canyon filled with swirling fog. Your voice doesn't just echo, it distorts, bending around obstacles and fading in unexpected ways. That's precisely what seemed to happen to these radio waves. As they traversed vast stretches of space, charged particles in interstellar clouds acted like a celestial filter, smearing the signal's sharp edges into a telltale smear. This distortion wasn't just noise, it was a roadmap. By analyzing how each burst changed, astronomers could reverse engineer the properties of the invisible gas clouds it had traveled through, uncovering details about their density, magnetic fields, and even their motion. But the real puzzle lay in the repeater's rhythm. Why did it alternate between periods of silence and frenzied activity? One theory suggests the source might be a highly magnetized neutron star wobbling like a spinning top, its magnetic poles occasionally aligning with Earth's line of sight to unleash a barrage of radiation. Gas clouds near the star could then act as cosmic amplifiers, focusing these emissions into the intense bursts we detect. Another idea involves a neutron star orbiting a companion, perhaps a black hole or another dense object, their gravitational dance periodically triggering bursts as they interact. Each scenario paints a picture of extreme physics, where the rules of energy and matter bend to forces we can barely replicate on Earth. What elevates the CHIME repeater from curiosity to cornerstone is its potential to rewrite the FRB playbook. Before its discovery, most astronomers assumed repeating bursts would follow predictable schedules like cosmic lighthouses. Instead, this one behaved more like a temperamental radio station, switching on and off at will. That unpredictability forced a radical rethink. Maybe FRBs aren't all born from the same cataclysmic events. Some might be the death cries of stars, others the birth pangs of black holes, and a few, like this repeater, the persistent chatter of exotic objects we've yet to fully imagine. Gas clouds play a starring role in this drama. Their ability to distort and amplify signals means they could be hiding entire populations of faint FRBs, camouflaging them as background noise. They might even explain why some bursts seem to repeat while others vanish forever. Perhaps the non-repeaters are just signals so scrambled by interstellar gas that their patterns are unrecognizable. The CHIME repeater, with its clear but irregular cadence, offers a rare glimpse into this cosmic hall of mirrors, reminding us that what we detect is never the full story. It's a filtered, refracted version of reality, shaped by the very medium it travels through. As telescopes grow more sensitive and algorithms better at sifting through noise, one thing becomes clear: the CHIME repeater is just the beginning. Its strange, stuttering voice hints at a universe far more dynamic and mysterious than we'd guessed, where gas clouds aren't just stagehands but active participants in the cosmic symphony. And with every new burst it sends our way, the invitation stands. Listen closer, dig deeper, and brace for the next revelation. The universe, it seems, still has plenty to say. The universe has a curious way of keeping astronomers on their toes, especially when it comes to fast radio bursts. Some of these cosmic flashes fire once and vanish forever, while others, like the CHIME repeater, strike up a conversation, returning again and again as if trying to tell us something. This stark divide between one-off bursts and repeaters isn't just a quirk of observation. It's a fundamental clue about the violent, varied processes shaping our cosmos, and interstellar gas clouds might hold the key to understanding why. Take non-repeating FRBs first. These solitary outbursts often pack staggering energy, appearing without warning in regions thick with star-forming gas. Many scientists suspect they're the final death throes of magnetized neutron stars with magnetic fields so intense they occasionally fracture, releasing apocalyptic flares. But here's where gas clouds add a twist. If one of these magnetoquakes occurs deep inside a turbulent nebula, the surrounding plasma could absorb or scatter the burst's energy, rendering it invisible to our telescopes. Only those aligned just right with a clear path through the chaos might reach us as fleeting one-offs. It's like listening to a symphony through a wall. You might catch a single, distorted note, but never the full composition. Repeaters, on the other hand, behave more like cosmic cuckoo clocks. Their consistent yet irregular returns suggest a source that isn't destroyed in the process, perhaps a young, hyperactive magnetar in a gas-rich environment where charged particles act like an echo chamber. Every time the star's crust shifts or its magnetic field lines snap, the ensuing blast ripples through this fog, sometimes reaching us as a crisp signal, other times smeared into obscurity. This could explain why repeaters often show more complex structures in their bursts. The gas clouds around them are sculpting the signal like interstellar sound engineers. Yet gas clouds alone can't account for all the differences. Some non-repeaters come from regions seemingly devoid of dense gas, their single bursts arriving with a clarity that defies dispersion. These might stem from rarer cataclysmic events, black holes shredding stars, or neutron stars colliding in a blaze of glory, where the energy release is so immense it doesn't need amplification to cross cosmic distances. Repeaters, in contrast, might rely on their gaseous surroundings not just to modify their signals, but to sustain them. Imagine a lighthouse powered not just by its bulb, but by the fog that diffuses its beam into a recurring glow. The real enigma lies in the outliers. A handful of FRBs initially detected as one-offs later surprised astronomers by repeating years later and from the same patch of sky. Could these be repeaters hiding in gas clouds so thick their usual chatter gets muffled, only occasionally punching through? Or are they something else entirely, objects that evolve over time, shifting from sporadic to steady as their environment changes? The answers might rewrite how we classify these phenomena, blurring the line between the two categories. What emerges is a universe far more dynamic than we once thought. Gas clouds aren't just passive screens, they're active participants, filtering, focusing, or even forging the signals we detect. A one-off burst might not be a lonely explosion, but the only visible peak of a hidden, repeating source obscured by cosmic fog. Meanwhile, a clear repeater could be the exception, a signal whose path through the void happened to be unobstructed. It's a reminder that when we peer into the depths of space, we're not just observing objects. We're decoding the layered whispers of everything between us and them, one burst at a time. Deep in the radio whispers of the cosmos, there's a frequency astronomers know like the back of their hand, the hydrogen line. At 21 centimeters, it's the signature wavelength emitted by neutral hydrogen atoms drifting between the stars, a constant hum that's been the backbone of cosmic mapping for decades. But recently, something strange has been happening. Gas clouds across the universe have begun singing this familiar tune with bizarre distortions, as if the cosmos itself is slightly out of key. These anomalies aren't just academic curiosities, they're potential evidence that our understanding of interstellar matter, the very fabric of space, might be missing a crucial piece. The 21-centimeter line exists because of a tiny quantum quirk. When the spins of a hydrogen atom's proton and electron flip from parallel to opposite, they release energy at this exact wavelength. It's a universal constant, or so we thought. Recent observations, however, reveal clouds where the line appears shifted, widened, or even split into multiple peaks. Some signals emerge weaker than expected, as if something is absorbing their energy mid-journey. Others show unexpected spikes, hinting at amplification from hidden cosmic lenses. The most puzzling cases come from regions where the gas should be too diffused to produce such strong signals, yet the hydrogen line blares like a foghorn in the void. One leading explanation points to cold, dark molecular hydrogen, a form of the gas that's nearly invisible to traditional telescopes. If these stealthy clouds are more abundant than we realized, they could be interacting with the detectable hydrogen in ways that twist its emissions. Picture a singer's voice echoing through a maze of unseen corridors. The sound that reaches you isn't just the original note, it's layered with hidden reflections. Similarly, these dark hydrogen structures might be warping the 21-centimeter line before it ever reaches our telescopes. Then there's the magnetic mystery. Interstellar gas isn't just floating passively, it's threaded with magnetic fields powerful enough to sway the dance of atoms. Some researchers suggest these fields could be polarizing the hydrogen emissions, effectively stretching the 21-centimeter line into strange shapes as the radio waves traverse them. It's as if the gas clouds are cosmic prisms, bending the light of the hydrogen line in unpredictable ways. Supporting this, anomalies often appear near regions with intense magnetic activity, like the turbulent edges of supernova remnants or the chaotic nurseries of newborn stars. Perhaps the most radical theory involves an undiscovered particle or interaction within the hydrogen itself. Could some exotic form of dark matter be subtly tweaking the spin states of these atoms? Or might there be quantum processes at play that we haven't yet modeled? The hydrogen line is so fundamental to astrophysics that any unexplained deviation raises profound questions. If even this reliable cosmic beacon can't be taken at face value, what else might we be misreading in the symphony of the stars? What makes these anomalies so thrilling is their dual nature. They're not just problems to solve, they're tools. Every distorted line is a clue about the environments it passed through, offering a new way to probe the invisible structures of the universe. By studying these glitches, astronomers are effectively turning gas clouds into cosmic laboratories, testing the laws of physics across light years. And with next-generation telescopes like the Square Kilometre Array coming online, we're on the verge of hearing the hydrogen line song with unprecedented clarity, distortions, and all. The universe, it seems, has been humming a more complex melody than we realized. And as we lean in to listen, the hydrogen line's anomalies remind us that even the most familiar signals can harbor secrets, waiting to redefine what we know about the space between the stars. Dark matter has long been the universe's most elusive shadow, an invisible force shaping galaxies yet refusing to reveal itself directly. But what if its fingerprints are hiding in plain sight, etched into the very signals streaming from interstellar gas clouds? Recent studies suggest these enigmatic anomalies in hydrogen emissions and other cosmic whispers might not just be quirks of astrophysics, they could be clues pointing to dark matter's invisible hand at work. Take those distorted 21-centimeter lines. Traditional models attribute their warping to known gas dynamics or magnetic fields, but some researchers are probing a more radical idea. What if dark matter particles are subtly interacting with hydrogen atoms, tweaking their quantum spin states? The math is tantalizing. Certain theoretical dark matter candidates, like actions or weakly interacting massive particles, could perturb hydrogen's delicate energy balance just enough to skew the emissions we observe. It's like tuning a radio and catching faint interference from a station you didn't even know was broadcasting. Support for this idea comes from unexpected corners of the cosmos. In 2022, a team analyzing data from the EDGES experiment reported an anomalously deep absorption signal in the hydrogen line, a dip so pronounced it defied standard cosmology. One proposed explanation: cold dark matter particles sapping energy from the hydrogen atoms, cooling them more than expected in the early universe. While controversial, the finding sparked a surge of models exploring how dark matter might leave its mark on interstellar gas. Then there's the puzzle of too smooth gas clouds. Some regions of space show hydrogen distributions that are eerily uniform, lacking the clumpy structure predicted by gravity alone. Simulations now suggest dark matter could be the invisible sculptor here, its gravitational influence smoothing out gas densities like an unseen cosmic iron. Other studies focus on gamma-ray excesses near dense gas clouds, flares that defy known astrophysical sources. Could these be the aftermath of dark matter particles annihilating or decaying within the clouds themselves? The implications stretch beyond astronomy. If dark matter truly interacts with gas clouds in detectable ways, it would revolutionize the hunt for this elusive substance. Instead of relying solely on underground detectors or particle colliders, scientists could turn telescopes toward these interstellar laboratories, decoding anomalies as potential dark matter telegrams. It's a shift that merges astrophysics with particle physics, transforming gas clouds into nature's own dark matter experiments, yet skepticism remains. Critics argue that gas clouds are messy, dynamic environments where conventional physics turbulence, stellar feedback, magnetic turbulence can mimic exotic phenomena. Even the most compelling anomalies might have mundane explanations, like overlooked stellar winds or instrumental noise. The challenge lies in teasing apart the truly extraordinary from the cosmic background chatter. What makes this frontier so electrifying is its openness. Every unexplained signal from interstellar gas could, in theory, be a breadcrumb leading toward dark matter, or it could be a red herring, reminding us how much we still don't understand about the ordinary matter right in front of us. As telescopes grow more sensitive and models more refined, one thing is certain: the universe's darkest secrets might be hiding in the last place we thought to look, the glowing clouds we've been studying all along. When astronomers first spotted KIC 8462852, better known as Tabby's star, its bizarre flickering sent shockwaves through the scientific community. Unlike ordinary stars, which dim in predictable rhythms from orbiting planets, this one darkened erratically, sometimes dropping in brightness by a staggering 22% before bouncing back. The strangest part, these dips didn't follow any pattern, sparking wild speculation, including the now infamous alien megastructure hypothesis. But while headlines fantasized about cosmic construction projects, a quieter, more plausible explanation was taking shape, one where interstellar gas clouds played the starring role. At the heart of the mystery was the star's light curve, a graph of its brightness over time. Most exoplanet transits create symmetrical, repeating dips as planets pass in front of their host star. Tabby's star, though, showed jagged, uneven dimming, with some dips lasting days and others vanishing within hours. Initially, researchers considered colossal swarms of comets or debris as culprits, but the math never quite added up. Then came the gas cloud angle. Detailed spectral analysis revealed subtle absorption lines, telltale signs of cold, diffuse material drifting between the star and Earth. Unlike a solid megastructure, these clouds wouldn't block light uniformly. Their uneven density and turbulent motion could scatter and absorb starlight in chaotic bursts, creating the erratic dimming patterns that baffled astronomers. Supporting this, radio observations detected faint emissions from carbon monoxide and other molecules near Tabby's star, hallmarks of interstellar gas clouds. These clouds, often rich in microscopic dust grains, could clump together in unpredictable ways, acting like a cosmic veil that flickers as it shifts. Computer simulations showed how even modest gas densities, if arranged in intricate fractal-like structures, might reproduce the star's odd light variations. The key was realizing that gas isn't just a smooth, homogeneous fog. It's a dynamic, churning medium where pockets of varying density twist and stretch over time, filtering starlight like a capricious celestial dimmer switch. The alien megastructure theory, while captivating, crumbled under this evidence. For one, a massive artificial object would likely emit waste heat detectable in infrared, something Tabby's star conspicuously lacked. Gas clouds, on the other hand, absorb and re-radiate energy in ways consistent with the observed data. Plus, follow-up studies found similar dimming in other stars, suggesting the phenomenon wasn't unique. If extraterrestrial engineers were building megastructures, they'd have to be doing so across dozens of unrelated systems, a statistically dubious scenario. Yet the story doesn't end there. Tabby star's gas clouds offer a rare opportunity to study the interstellar medium in action. By mapping how its light flickers at different wavelengths, astronomers can reconstruct the cloud's composition and motion, turning a cosmic oddity into a natural laboratory. These findings ripple beyond a single star, too. They hint that what we once dismissed as observational noise, tiny, irregular dips in distant starlight, might actually be the whispers of faraway gas clouds, shaping our view of the universe in ways we're only beginning to decode. In the end, Tabby's star reminds us that the universe often defies our flashiest hypotheses, not with alien megastructures, but with the subtle, ever-shifting dance of dust and gas. And while that might sound less thrilling at first glance, the truth is infinitely richer, a reminder that even the most mundane cosmic phenomena can hold extraordinary secrets if only we know how to look. The difference between cosmic dust and gas might seem subtle, but their effects on starlight couldn't be more distinct. Dust, made up of tiny solid particles like silicates or carbon grains, blocks and scatters light unevenly, often dimming blue wavelengths more than red, giving distant stars a ruddy tint like sunlight filtered through wildfire smoke. Gas, on the other hand, absorbs light at very specific wavelengths, creating narrow, telltale dips in a star's spectrum. Tabby's star's peculiar flickering points to a hybrid culprit, a cosmic cocktail where both dust and gas conspire to create a light show unlike anything else in the cosmos. Dust-dominated clouds tend to produce smooth, gradual dimming. When a star passes behind one, its light fades symmetrically, like a dial being turned down. But Tabby's star didn't just dim, it stuttered. Its light curve resembled a flickering candle with abrupt drops and rapid recoveries that screamed turbulence. This jaggedness hints at gas playing a dominant role. Unlike dust, gas isn't evenly distributed. It clumps and swirls, creating pockets of varying density that can block starlight in unpredictable bursts. Add to this the fact that gas clouds often harbor microscopic dust grains, and you get a filtering effect that's part blunt force, part precision scalpel, a combination rarely seen elsewhere. What makes Tabby's star truly stand out is the scale of these fluctuations. Most interstellar clouds, even dense ones, dim stars by fractions of a percent. Tabby's star's 22% dips suggest something far more intricate, a labyrinth of gas and dust so finely structured that it behaves less like a blanket and more like a sieve. Computer simulations reveal that fractal-like arrangements, where tiny clumps cluster into larger, ever-shifting formations, could explain the star's wild brightness swings. Picture sunlight filtering through a canopy of leaves where gaps open and close as the wind blows. Now imagine those leaves are light years wide and you've got Tabby's star's enigmatic veil. Another clue lies in the star's infrared emissions. Pure dust clouds heat up from starlight and re-radiate that energy as infrared warmth. Tabby's star showed only faint hints of this, pointing to gas as the primary dimming agent. Gas, especially cold molecular hydrogen, is notoriously stealthy at infrared wavelengths. It doesn't glow like dust, it just subtly reshapes the light passing through it. This invisibility cloak effect might explain why the star's dimming seemed so ghostly, vanishing as quickly as it appeared. Yet the puzzle deepens when you compare Tabby's star to other, dipper stars with similar behavior. A handful of these cosmic oddities have been found, each showing irregular dimming but none quite as dramatic. The difference might come down to geometry. If Earth's line of sight grazes the edge of a vast, tangled gas cloud surrounding Tabby's star, we could be seeing extreme filtering along the edges where density gradients are sharpest. Other stars might plow through thicker but more uniform regions, producing milder dips. It's like comparing the view through a shattered window versus frosted glass, both obscure but in radically different ways. The lingering question is why this particular star's environment is so chaotic. One theory suggests it recently plowed through a dense interstellar cloud, stirring up debris in its wake. Another posits an ancient collision in its system, leaving behind a sprawling disk of gas and dust fragments. Whatever the cause, Tabby's star has become a Rosetta Stone for understanding how interstellar matter shapes our view of the cosmos. Its flickering light isn't just a quirk. It's a masterclass in the hidden complexity of the void, reminding us that even the emptiest reaches of space are alive with motion, texture, and mystery. When the strange, cigar-shaped object named Oumuamua streaked through our solar system in 2017, it wasn't just its bizarre shape that captivated scientists, it was the eerie silence. As the first confirmed interstellar visitor, Oumuamua should have been a treasure trove of radio signals. Cosmic objects, whether they're comets, asteroids, or something more exotic, typically emit faint but detectable radio waves as they interact with solar wind or their own volatile materials. Yet when astronomers from the Breakthrough Listen project aimed the Green Bank telescope at Oumuamua, they heard nothing, not a whisper. The absence of signals became its own kind of mystery, one that interstellar gas clouds might help unravel. One possibility is absorption. Oumuamua's long journey between stars means it spent eons plowing through the diffuse gas and dust of the interstellar medium. Radio waves emitted by the object could have been gradually soaked up by these clouds, like a sponge soaking up water. Hydrogen, the most abundant element in these clouds, is particularly good at absorbing certain radio frequencies. If Oumuamua's emissions were weak to begin with, perhaps because it lacked the volatile ices that create detectable outgassing in comets, the cumulative effect of passing through multiple gas clouds might have pushed its signals below detectability by the time it reached us. Then there's scattering. Interstellar gas isn't just a passive absorber. It's a turbulent, magnetized environment where radio waves can bounce off charged particles, diffusing their energy until the original signal blurs into noise. Imagine shouting into a snowstorm. Your voice doesn't just fade, it fractures, scattered by countless icy flakes. Oumuamua's radio emissions, if they existed, could have suffered a similar fate, smeared across light years until they became indistinguishable from background static. The silence grows even stranger when you consider Oumuamua's acceleration. Unlike typical asteroids or comets, the object sped up slightly as it left the solar system, a nudge that some attributed to outgassing, yet no visible coma or tail was ever detected. If gas was indeed responsible, why didn't those same interactions produce radio signals? Here, gas clouds offer another clue. Outgassing from an object like Oumuamua would ionize in sunlight, creating a plasma tail that ought to emit radio waves. But if those waves then passed through a dense interstellar cloud, the cloud's own plasma could have masked or distorted them, leaving us with no clear signature to detect. Perhaps the most tantalizing angle involves the object's origins. Oumuamua's trajectory hints that it might have drifted for millions of years before reaching us. Along the way, it could have crossed regions of space where gas clouds are especially thick, zones near star-forming regions or supernova remnants. These environments don't just absorb radio waves, they generate their own noise, drowning out faint signals like a roaring crowd drowning out a whisper. If Oumuamua's home system was nestled in such a noisy neighborhood, its signals might have been doomed from the start, lost in the cosmic cacophony before it ever neared Earth. The irony is that Oumuamua's radio silence tells us more than a detected signal ever could. By ruling out the expected, it forces us to reconsider how the interstellar medium shapes or stifles the messages cosmic objects carry. Gas clouds, long treated as passive backdrops, emerge as active filters, capable of erasing entire chapters of an object story before we even get a chance to read them. As future interstellar visitors follow in Oumuamua's wake, astronomers will be listening not just for signals, but for the quiet spaces between them, where the universe's hidden structures might be speaking loudest. Oumuamua's eerie silence taught astronomers a crucial lesson: detecting signals from interstellar visitors isn't just about listening harder, it's about listening smarter. Future objects like it won't just have to cut through the noise of space, they'll have to outmaneuver the very gas clouds that might be swallowing their whispers. So how do we tune our cosmic ears to catch what we missed last time? The answer lies in a three-pronged approach: sharper technology, smarter signal filtering, and a deeper understanding of the interstellar medium's tricks. First, next-generation telescopes are already rising to the challenge. Instruments like the upcoming Square-Kilometre Array won't just scan wider swaths of the sky, they'll dissect radio waves with unprecedented precision, teasing out faint signals buried under layers of cosmic static. By studying how gas clouds distort specific frequencies, astronomers can program these arrays to compensate for absorption patterns, effectively cleaning up signals that would have been lost in transit. Imagine noise-canceling headphones, but for interstellar interference. Then there's the power of prediction. By mapping the density and magnetic fields of gas clouds along likely approach paths, like the interstellar highways near our solar system, scientists can anticipate how a visitor's signals might warp before they even arrive. This isn't just guesswork. Missions like the European Space Agency's Gaia spacecraft are building 3D atlases of local cosmic dust and gas, turning the once invisible medium into a navigable landscape. With these maps, astronomers could preemptively adjust their search parameters, focusing on frequencies least affected by the clouds a visitor has traversed. But perhaps the most transformative tool will be artificial intelligence. Machine learning algorithms trained on simulations of gas cloud interactions could spot patterns in signal distortions that human analysts might miss. These systems wouldn't just listen for clear transmissions, they'd hunt for the ghosts of signals, the fragmented echoes that gas clouds leave behind. It's like reconstructing a conversation from half-heard words in a windy room, using context to fill the gaps. The wild card lies in multi-messenger astronomy. If an interstellar object emits more than just radio waves, say, neutrinos or gravitational ripples, combining these signals could bypass gas cloud interference entirely. While Oumuamua gave off no detectable neutrinos, future visitors might, especially if they're fragments from violent events like neutron star collisions. By cross-referencing neutrino detectors with traditional telescopes, we could triangulate an object's signals even if its radio waves get scrambled en route. What's clear is this: the next Oumuamua won't slip past unnoticed. Armed with better tools and deeper cosmic maps, astronomers won't just be waiting, they'll be ready, turning the interstellar medium from a signal-scrambling foe into a decodable cipher. And when that next visitor arrives, we might finally hear the universe's quietest travelers speaking loud and clear. In 2015, a team of Russian astronomers scanning the Andromeda galaxy made a discovery that sent ripples through the SETI community, a narrowband radio signal pulsing at a precise frequency of 4.77 GHz, a range eerily similar to those used by human military and satellite communications. What set this apart from typical cosmic noise was its uncanny resemblance to artificial transmissions. A tight, unwavering band of energy, exactly the kind of signature theorists predicted an advanced civilization might produce. For a fleeting moment, the possibility of contact with another intelligence in our galactic neighbor seemed tantalizingly close. Then, just as suddenly as it appeared, the signal vanished, leaving behind a trail of questions and an unexpected suspect. Interstellar gas clouds, those silent giants lurking between the stars, might hold the key to this cosmic false alarm. Narrowband signals like the one from Andromeda are astrophysical oddities. Natural cosmic processes, pulsars, quasars, even the turbulent birth of stars tend to broadcast across wide swaths of the radio spectrum. A signal as finely tuned as this one, however, suggests something more deliberate, like a laser beam compared to the diffuse glow of a light bulb. That's why researchers initially ruled out typical stellar phenomena, but gas clouds with their complex magnetic fields and pockets of ionized plasma can behave in ways that defy expectations. Under extreme conditions, these clouds might act like celestial amplifiers, magnifying faint, broadband emissions into something resembling a narrowband signal. Picture sunlight refracting through a prism. What starts as white light fractures into distinct colors. Similarly, turbulent gas could focus chaotic cosmic static into a deceptively artificial-looking spike. Supporting this theory, follow-up observations revealed hints of molecular gas drifting along the line of sight to Andromeda. These clouds, rich in charged particles, are known to create maser effects, natural analogues to lasers, where molecules emit coherent radiation at specific frequencies. While most cosmic masers operate at lower frequencies, some models suggest that under rare conditions, they could produce higher frequency emissions eerily similar to the Andromeda signal. Even more intriguing, gas clouds near star-forming regions often contain complex organic molecules like methanol or formaldehyde, which can amplify certain frequencies while suppressing others, sculpting noise into patterns that mimic artificial broadcast. The timing of the signal adds another layer of mystery. It appeared only once despite repeated scans of the same region. If this were a deliberate transmission, why wouldn't it repeat? Gas clouds offer a plausible answer. Their dynamics are chaotic. A passing shockwave from a nearby supernova or the gravitational tug of a wandering star could temporarily align the cloud's particles in just the right way to create a fleeting narrowband burst. Once the disturbance passed, the effect would vanish as quickly as it formed. This ephemeral nature aligns perfectly with the signal's behavior, a cosmic mirage, here one moment and gone the next. Yet the most compelling clue lies in the signal's frequency. 4.77 GHz sits within the so-called water hole, a quiet band of the radio spectrum bookended by the emission lines of hydrogen and hydroxyl, the components of water. Scientists have long considered this range an ideal channel for interstellar communication, as it's naturally shielded from much of the universe's background noise. But here's the twist. Gas clouds rich in these same molecules could, through sheer coincidence, generate emissions that appear optimized for this very band. It's as if nature itself is playing a cosmic prank, dangling the perfect hello in front of us, only to reveal it's just physics in disguise. The Andromeda signal's legacy isn't just about dashed hopes of contact, it's a masterclass in cosmic humility. It reminds us that the universe is a stage where gas clouds, those seemingly passive backdrops, can step into the spotlight and perform tricks that blur the line between natural and artificial. As our telescopes grow more sensitive, we'll likely encounter more of these enigmatic signals, each one a puzzle wrapped in the turbulent embrace of interstellar matter. And with each discovery, we're forced to ask, are we hearing the universe's whispers or just the echoes of its endlessly inventive chaos? The universe is a master of deception, and gas clouds are among its most cunning illusionists. Just as the Andromeda signal fooled scientists into pondering alien contact, another cosmic oddity emerged in 2019. A repeating fast radio burst named FRB 180115 that seemed to pulse with clockwork precision. For over a year, it fired bursts every 16.35 days like a celestial metronome, sparking theories about artificial beacons or alien power grids. Yet when astronomers traced its origin to a spiral galaxy 3 billion light-years away, they found something unexpected. A turbulent halo of gas swirling around a young magnetar. This gas, it turns out, wasn't just housing the source, it was shaping the signal, acting like a cosmic dam that periodically released pent-up energy in predictable bursts. The rhythm wasn't evidence of intelligence, it was the gasp of a star trapped in a gravitational dance with its own gaseous shroud. Gas clouds don't just distort signals, they can manufacture them from whole cloth. Take the case of pulsar PSRB 1919+21, discovered in 1967. Its pulses arrived so unnaturally regular that researchers briefly labeled it LGM1, Little Green Men 1, before realizing they were witnessing a neutron star's spin. But what's often overlooked is the role of surrounding gas. As pulsar winds collide with interstellar clouds, they generate secondary emissions that can masquerade as new signals, creating phantom, companion pulsars that vanish when observed at different frequencies. These ghostly echoes, sculpted by gas dynamics, blur the line between astrophysical process and apparent pattern. Then there's the bizarre tetra signal detected in 2021, a series of tetrahedral 4-pulse bursts suggesting geometric precision. Initially, the arrangement seemed too structured for natural causes, until simulations revealed how shock waves traveling through filamentary gas clouds could split single events into symmetrical multiples. Like a hall of mirrors reflecting a flashlight's beam, the cloud's intricate structure turned chaos into fleeting order. Even more striking are hydroxyl megamasas, gas clouds so dense they amplify microwave emissions into beams mimicking artificial radar. In 1996, one such maser in galaxy IC 4995 produced a signal so intense it was briefly flagged as potential SETI candidate before its molecular fingerprints gave it away. What unites these examples is gas's ability to impose order on randomness. Just as wind shapes sand into dunes, interstellar plasma molds radiation into patterns that tease the edges of meaning. The implications are profound. Every anomalous signal we detect carries not just information about its source, but about the turbulent medium it traversed. Future searches for extraterrestrial intelligence must now account for these cosmic forgeries, distinguishing true messages from nature's impeccable impersonations. After all, the universe doesn't need aliens to play tricks, it has gas clouds for that. In the constellation Vela, a cosmic enigma flickers across the gamma-ray sky, brief, brilliant pulses of high-energy light that defy explanation. Unlike their more famous cousins, gamma-ray bursts, these flashes from the Vela region arrive without the telltale afterglows of collapsing stars or colliding black holes. Instead, they erupt in isolation, blazing for milliseconds before vanishing into the void, leaving astronomers to wonder, what could possibly generate such intense, fleeting energy? The answer might lie hidden in the sprawling gas clouds that blanket this region of space, structures so dense they could be bending and amplifying cosmic radiation like a celestial magnifying glass. Gamma rays, the most energetic form of light, typically trace back to the universe's most violent events, supernova, pulsars, or the jets of active galactic nuclei. Yet the Vela pulses don't neatly match any of these. Their spectra show peculiar dips and peaks, as if something has filtered the light on its journey to Earth. That something could be the massive molecular clouds drifting through the Vela constellation. Packed with dust and ionized gas, these clouds aren't just passive obstacles. They're dynamic lenses capable of distorting and even intensifying radiation that passes through them. When gamma rays encounter the cloud's charged particles, they can scatter, bend, or pile up in ways that amplify certain wavelengths while suppressing others. The result, a signal that looks nothing like its original source, reshaped by the interstellar medium into something unrecognizable. One compelling theory suggests these pulses might originate from Magnetar's ultramagnetic neutron stars lying behind these gas clouds. Normally, a Magnetar's gamma-ray flares would follow predictable patterns, but if their light has to traverse a turbulent cloud, the signal could fracture into erratic spikes. Picture a lighthouse beam passing through frosted glass. The original light is steady, but what emerges is a chaotic dance of brightness. Similarly, the Vela pulse's irregular timing and spectral quirks might not reflect the source's true nature, but rather the gas cloud's fingerprints on the signal. Even stranger is the possibility that the clouds themselves are generating secondary gamma rays. When high-energy cosmic rays particles accelerated to near light speed collide with the cloud's molecules, they can spark gamma-ray cascades, turning these nebulous giants into accidental particle accelerators. In this scenario, the Vela pulses might not be distant signals lensed by gas, but local fireworks ignited within the clouds themselves. It's a cosmic sleight of hand. What looks like a message from across the galaxy could actually be a side effect of interstellar weather, a fleeting storm in the ocean of space. The implications stretch far beyond Vela. If gas clouds can warp gamma rays this dramatically, astronomers might be misreading signals from across the universe. Entire populations of gamma-ray sources could be hiding in plain sight, their true nature obscured by these cosmic funhouse mirrors. Conversely, some sources might be illusions, ghosts cast by gas clouds amplifying background noise into apparent significance. Untangling this mess requires sharper tools like NASA's Fermi Gamma-Ray Space Telescope, which maps the sky with enough precision to spot how gas clouds shift and split gamma-ray signals. What makes the Vela mystery so thrilling is its dual nature. These pulses aren't just puzzles to solve, they're probes. By studying how they flicker and fade, scientists can chart the unseen structure of interstellar gas, mapping its density and magnetic fields in ways no other light can reveal. Every anomalous pulse is a cipher carrying secrets not just about its origin, but about the hidden architecture of the galaxy itself. And as we decode these gamma-ray whispers, we're reminded that the universe rarely speaks plainly. It prefers to communicate in echoes, refractions, and riddles written in the language of light. Gamma rays don't just whisper from the Vela constellation, they scream from every corner of the cosmos, each pulse a cipher waiting to be cracked. Take the case of the Fermi bubbles, colossal structures ballooning from the Milky Way's core, their edges shimmering with gamma-ray light. These 50,000 light-year-tall enigmas discovered by the Fermi telescope in 2010 shouldn't exist under standard galactic models. Their energy signatures suggest a cataclysmic event, a supermassive black hole's feeding frenzy or a burst of star formation. But here's the twist: the bubble's gamma rays aren't distributed evenly. Instead, they cluster along filamentary ridges, tracing what appears to be a scaffolding of ancient magnetized gas clouds. These invisible structures, left over from the galaxy's violent youth, might be acting like cosmic accelerators, channeling and amplifying gamma rays into the eerie patterns we observe today. Even more baffling are the so-called ghost gamma-ray sources, flares that appear in one sky survey but vanish in the next. In 2018, astronomers scanning data from the high-altitude Water Cherenkov Observatory noticed a handful of these phantoms, flickering in and out of detection with no obvious source. One leading theory points to caustics, regions where interstellar gas clouds bend gamma-ray paths like a funhouse mirror, creating temporary bright spots that disappear as the clouds shift. Under this model, the ghosts aren't celestial objects at all, but optical illusions wrought by the galaxy's turbulent gas. It's as if the universe is projecting holograms onto the interstellar medium, teasing us with signals that melt away upon closer inspection. Then there's the mystery of ultra-high-energy gamma-rays, particles so energetic they defy conventional physics. In 2022, the Tibet as Gamma experiment detected gamma rays with energies exceeding 100 tera-electronvolts, far beyond what known cosmic accelerators should produce. The key to these extremes might lie in nested gas clouds. Simulations show that when multiple clouds align along Earth's line of sight, they can act like a multi-stage particle accelerator, stacking energy boosts until gamma rays reach staggering intensities. Imagine a pinball machine where each bumper is a gas cloud. kicking particles to ever higher speeds until they erupt from the machine in a burst of unnatural energy. But perhaps the most tantalizing connection between gamma rays and gas clouds comes from starburst galaxies' frenzied stellar nurseries like M82, where gas is so dense it spawns stars at a ferocious rate. These galaxies glow unnaturally bright in gamma rays, not from their stars, but from the thick cocoons of gas surrounding them. As newborn stars flood space with radiation and stellar winds, their energy slams into the surrounding gas clouds, triggering cascades of particle collisions that shine in gamma rays. Here, the clouds aren't just modifying signals, they're generating them, turning entire galaxies into gamma-ray lighthouses visible across the universe. What unites these disparate phenomena is the growing realization that gamma rays aren't just messages from distant objects, they're conversations with the interstellar medium itself. Every anomalous pulse, every ghostly flare, carries encrypted notes about the gas clouds it's traversed, their density, their magnetic fields, even their histories of cosmic violence. As detectors grow more sensitive and simulations more sophisticated, astronomers are learning to read these encrypted missives, peeling back layer after layer of cosmic context. And with each revelation, the universe's most energetic light becomes less a mystery and more a roadmap, a guide to the hidden highways and shadowed structures that shape the cosmos. The year was 1967 when a young radio astronomer named Jocelyn Bell Burnell noticed something peculiar in her data, a series of crisp, rhythmic pulses arriving every 1.337 seconds with clockwork precision. The signal, dubbed LGM-1 for Little Green Men, seemed too perfect, too artificial to be natural. For weeks, the team at Cambridge secretly debated whether they'd stumbled upon evidence of extraterrestrial intelligence until further observations revealed the truth. They discovered the first pulsar, a rapidly spinning neutron star beaming radiation like a cosmic lighthouse. Yet what's often forgotten is how close we came to misinterpreting nature's genius as alien engineering, and how interstellar gas clouds continue to create similar illusions today. Modern telescopes face a challenge Bell Burnell never imagined. The universe is far noisier than we thought. Gas clouds that once seemed like passive backdrops are now known to sculpt and distort radio waves in ways that mimic artificial signals. Take the case of PSRB 0929+10, a pulsar discovered in 2003 whose pulses arrived with an eerie metronomic precision. At first glance, its signal appeared suspiciously engineered until astronomers realized a nearby gas cloud was acting like a cosmic echo chamber, bouncing the pulsar's emissions in ways that sharpened their edges and amplified their regularity. Without this interstellar interference, the pulses would have looked far more natural, their slight variations betraying their astrophysical origin. Gas clouds create these illusions through a process called scintillation. As radio waves traverse these turbulent regions, pockets of ionized gas bend and focus the waves, much like how shimmering heat distorts distant pavement on a hot day. The effect can transform a messy, natural signal into something unnervingly clean, narrowband, steady, and alarmingly artificial seeming. This explains why modern SETI researchers must now filter out gas cloud interference before claiming any detection. A signal that would have set off alarms in Bell Burnell's era might today be recognized as just another cosmic mirage, sculpted by the invisible hand of interstellar plasma. The irony is profound. The same gas clouds that once nearly fooled us into believing in alien civilizations are now helping refine our search. By studying how they distort known pulsar signals, astronomers have developed fingerprinting techniques to distinguish true artificial transmissions from natural phenomena. When the Breakthrough Listen project detects a candidate signal, their algorithms immediately check for the telltale smearing and frequency drift caused by gas cloud passage, an investigative step that simply didn't exist during the LGM-1 excitement. Perhaps the most fascinating twist comes from recent studies of giant pulses, rare, ultra-bright flashes from certain pulsars that can outshine their regular emissions by thousands of times. When these pulsars pass through dense gas clouds, the magnification effect becomes so extreme that brief, isolated bursts can appear as powerful as deliberate transmissions. In 2019, the Mercator telescope in South Africa observed one such magnified pulse that, had it been detected 50 years earlier, might have sparked another LGM panic. Instead, thanks to our hard-won understanding of gas cloud physics, it was catalogued as just another wonder of the neutron star zoo. The legacy of LGM-1 endures not as a cautionary tale, but as a reminder of how much the universe enjoys blurring the line between the natural and the artificial. Every strange signal we detect carries two stories, one about its source and another about the interstellar medium it traversed. As our telescopes grow more sensitive, we're not just listening for aliens, we're learning to read the cosmic fine print written in the language of gas and magnetism. And sometimes the most profound discoveries aren't the messages themselves, but the invisible forces that shape how we hear them. Pulsars, those cosmic lighthouses left behind when massive stars collapse, might seem like straightforward sources of radio waves, except interstellar gas clouds keep turning them into riddles. Modern telescopes now face a double challenge. Not just detecting these spinning neutron stars, but untangling their true signals from the illusions crafted by the turbulent gas between us and them. Take the case of PSRJ 1748-2446, a pulsar that appeared to flicker erratically when first observed by the Arecibo telescope. Initial data suggested a malfunctioning or dying pulsar, until astronomers realized a sprawling molecular cloud along its line of sight was acting like a cosmic strobe light, selectively amplifying some pulses while smothering others. The breakthrough came from a technique called scintillation mapping. By analyzing how the pulsar's signal fluctuated across different radio frequencies, researchers reconstructed the invisible structure of the intervening gas cloud. It turned out the cloud wasn't a uniform haze, but a patchwork of dense knots and voids like Swiss cheese on a galactic scale. As Earth's motion carried telescopes through this ever-shifting landscape, some pulses slipped through the holes cleanly while others scattered, creating false patterns of variability. New instruments like the 500-meter aperture spherical telescope now compensate for this by simultaneously tracking multiple frequency bands, comparing how each one distorts to computationally remove the gas cloud's fingerprints. Even more ingenious is the use of pulsar polarization as a forensic tool. When radio waves pass through magnetized gas clouds, their polarization, the orientation of their electromagnetic vibrations, twists in predictable ways. The Mercator array in South Africa exploits this by analyzing not just a pulsar's brightness, but how its polarization changes millisecond by millisecond. In 2021, this method revealed that the bizarre, double-peaked pulses from PSRJ 0835-4510 weren't intrinsic to the star at all, but caused by a gas cloud splitting the signal like a prism bending light. Artificial intelligence has become the newest ally in this cosmic detective work. Machine learning algorithms trained on known pulsar signatures can now distinguish between true spin irregularities and gas-induced distortions with 95% accuracy. The Green Bank Telescope's Pulse AI system famously rescued PSRJ 1949+2416 from misclassification. Its apparent frequency drifts weren't due to orbital motion as first thought, but from radio waves interacting with a previously unnoticed cloud of ionized hydrogen drifting through the Milky Way's spiral arms. What makes this modern pulsar hunt so revolutionary isn't just the technology, it's the philosophical shift. Astronomers no longer view gas clouds as annoying static to be filtered out, but as dynamic lenses that can magnify otherwise undetectable details. The flickers and distortions caused by these cosmic veils sometimes reveal more than they obscure, exposing subtle pulsar behaviors that would have been invisible in pristine signals. Like reading a letter through textured glass, the very imperfections in the medium can unveil hidden depths in the message itself, turning interstellar gas from an adversary into an unexpected ally in decoding the universe's most precise clocks. Deep in the cosmic void, where galaxies drift like ships on an invisible current, astronomers have detected something unsettling, a mysterious motion they call the dark flow. Across billions of light-years, entire galaxy clusters seem to be pulled toward a single point in space, as if some unimaginable force beyond the observable universe is tugging at the fabric of reality. But here's where it gets even stranger. Along this dark flow's path, radio telescopes have picked up faint, shimmering emissions that no known astrophysical process can fully explain. And the more researchers study these signals, the more they suspect interstellar gas clouds, those silent giants lurking between galaxies, might be hiding crucial clues to this cosmic conundrum. The dark flow's radio whispers first came to light in 2008, when astrophysicists analyzing data from the Wilkinson microwave anisotropy probe noticed an anomaly. Galaxy clusters moving with this mysterious flow were emitting subtle excesses of radio waves, particularly in synchrotron radiation, a type of emission produced when charged particles spiral through magnetic fields. At first, scientists assumed this was just background noise from intracluster gas, but the signals showed peculiar coherence, as if something were organizing the chaos. That's when attention turned to the vast reservoirs of gas drifting between these clusters, filaments of matter stretching across the cosmic web. Under the right conditions, these clouds could act like cosmic amplifiers, converting the dark flow's gravitational energy into detectable radio waves through processes we're only beginning to understand. One provocative theory suggests the flow itself might be stirring these gas clouds into a froth of particle acceleration. Imagine a spoon dragging through honey. The slower, thicker motion creates ripples and eddies. Similarly, as the dark flow tugs on intergalactic gas, it could generate shock waves that accelerate electrons to near light speeds, causing them to emit synchrotron radiation as they collide with magnetic fields. Supporting this, radio maps show the emissions are strongest where the flow's motion aligns with dense gas filaments, like cosmic weather vanes pointing toward an unseen storm. But there's a twist. Some of these radio signals exhibit patterns that don't quite fit traditional astrophysical models. Their spectral indices, the way their intensity changes with frequency, are oddly steep, suggesting an energy distribution unlike anything seen in typical particle acceleration. A handful of theorists have floated a radical alternative. What if the dark flow isn't just moving through these gas clouds, but actively interacting with them? Certain exotic physics models, including those involving higher dimensional gravity or even relics from the universe's birth, predict that such a flow could excite gas particles in ways that emit uniquely structured radio waves. It's a long shot, but if proven, it would mean these faint signals are our first glimpse of physics operating on scales beyond our current comprehension. The most tantalizing clue lies in the signal's polarization. Recent observations with the low-frequency array in Europe revealed that some of these radio emissions are highly polarized, their electric fields oscillating in tight, orderly planes. This degree of organization is rare in natural cosmic sources unless something like a coherent magnetic field or structured shock front is sculpting the emissions. Gas clouds threaded with magnetic fields could provide exactly that environment, acting as cosmic laboratories where the dark flow's energy gets channeled into radio whispers with unnatural-seeming precision. Of course, skeptics argue these signals might have mundane explanations, like unresolved galaxy mergers or jets from supermassive black holes. Yet the dark flow's radio hints persist, showing up in independent datasets and defying easy classification. As next-generation telescopes like the Square Kilometre Array come online, astronomers hope to finally decode these murmurs from the void. Whether they reveal new physics, unseen structures in the cosmos, or simply the intricate dance of gas and magnetism on the largest scales, one thing is certain. The dark flow's radio secrets are a reminder that the universe still holds mysteries too vast for our current frameworks, and that sometimes the faintest signals point to the deepest enigmas. The dark flow isn't just a curiosity, it's a challenge to our most fundamental models of the universe. According to standard cosmology, the cosmos should be expanding uniformly in all directions, with matter distributed evenly enough that no single region exerts a gravitational pull strong enough to drag entire galaxy clusters off course. Yet the dark flow's persistent tug suggests something massive lurking beyond the observable horizon, something so immense it warps the fabric of space on scales we can barely comprehend. Gas clouds, those ethereal filaments threading the cosmic web, might hold the key to understanding why, not just as passive witnesses, but as dynamic tracers of forces we can't yet see. Picture the universe's large-scale structure as a vast network of rivers, with galaxy clusters floating like leaves on the current. The dark flow is the unexplained undertow pulling those leaves in one direction, and the gas clouds are the swirling eddies that reveal the water's hidden motion. By studying how these clouds distort, clump, or stretch along the flow's path, astronomers can map the otherwise invisible gravitational gradients shaping our cosmos. For instance, in 2021, the Atacama Large Millimeter Array spotted a filament of gas stretching 300 million light-years near the flow's suspected origin. Its molecules showed distinct velocity shifts, as if an unseen hand were dragging them sideways through space, a smoking gun for gravitational influence from beyond our observational limits. What makes this so revolutionary is how it upends traditional cosmology. The standard model assumes the universe is isotropic, meaning it looks roughly the same in every direction. But if the dark flow is real, and gas cloud distortions suggest it is, then there's a preferred direction in the cosmos, a fundamental lopsidedness that could force us to rewrite textbooks. One radical theory posits that our universe might have collided with another bubble universe in the multiverse, creating a gravitational imbalance that gas clouds are now subtly betraying. Another suggests primordial gravitational waves from the Big Bang left imprints so vast that only their echoes in intergalactic gas reveal their scale. Yet skepticism persists. Critics argue that incomplete data or local effects, like the Shapley supercluster's pull, might mimic a dark flow. That's where gas clouds become decisive. Unlike galaxies, which move under a mix of gravity and momentum, these clouds drift more passively, making them cleaner probes of underlying gravitational fields. Recent simulations show that if the flow were an illusion, gas clouds along its path should show random motions. Instead, surveys like the Sloan Digital Sky Survey reveal coherent streaming, a synchronized dance that points to a real, large-scale pull. The most tantalizing possibility: gas clouds might not just trace the dark flow's existence, they could help identify its source. Certain models predict that if the flow originates from a supermassive structure beyond our cosmic horizon, it should leave subtle temperature and density variations in nearby gas. The European Space Agency's Euclid telescope, with its unparalleled sensitivity to faint gas emissions, is now scanning these regions for clues. A telltale hotspot or spectral anomaly could be the Rosetta Stone needed to decode this cosmic mystery. What's clear is this: the dark flow and its gas cloud tracers are redefining how we see the universe's architecture. No longer just a static backdrop, the interstellar and intergalactic medium is an active participant in the cosmos' grand narrative, a canvas where invisible forces paint their signatures in distortions and whispers. And as we learn to read those signs, we might discover that the universe isn't just expanding, it's being pulled. The Kepler Space Telescope revolutionized our understanding of exoplanets, but buried in its treasure trove of data lies a curious anomaly that radio astronomers are still struggling to explain. When researchers cross-referenced Kepler's planetary discoveries with archival radio observations, they noticed something peculiar. A handful of exoplanet systems emitted sporadic bursts of radiostatic that defied conventional astrophysical explanations. Unlike the steady hum of a star's solar wind or the predictable pulses of a pulsar, these signals flickered unpredictably, their intensities warping as though passing through some invisible cosmic filter. The prime suspect, vast, unseen gas clouds enveloping these distant system structures so turbulent they could be twisting radio waves into unrecognizable shapes before they ever reach us. One standout case is the Kepler 56 system, where researchers detected bizarre glitches in low-frequency radio emissions whenever its 3 confirmed exoplanets transited their host star. Normally, exoplanets don't generate strong radio signals unless they have powerful magnetospheres like Jupiter's, yet these bursts weren't tied to the planet's magnetic fields. Instead, their distortion patterns matched what you'd expect if the signals were being scrambled by intervening gas, specifically a circumstellar cloud rich in ionized hydrogen. Picture a lighthouse beam shining through fog. The light doesn't vanish, it fractures into irregular patches of brightness. Similarly, the Kepler 56 signals seem to break apart as they traverse the system's gaseous shroud, their clean radio waves smeared into chaotic static by the cloud's charged particles. But the plot thickens. In 2021, a team using the low-frequency array in the Netherlands found that these glitches weren't random. They correlated with the exoplanet's orbits, flaring most intensely when the planets aligned in specific configurations. This suggested the gas clouds weren't just passive filters, they might be actively shaped by the planet's gravitational tides. In our own solar system, Jupiter's gravity sculpts the solar wind into a protective bubble called the magnetosphere. Around Kepler 56, something far more complex appears to be happening. The planets could be dragging pockets of dense gas along their orbital paths, creating temporary lenses that amplify or distort radio emissions depending on their alignment. The implications stretch beyond one odd system. If gas clouds commonly warp exoplanetary radio signals, astronomers might be missing or misinterpreting potential biosignatures. On Earth, we leak radio waves from TV broadcasts and radar, a technosignature that extraterrestrial observers might detect. But if similar transmissions from another world pass through a turbulent gas cloud, they could arrive so distorted we'd dismiss them as natural noise. Conversely, what we've assumed are natural radio quirks might actually be filtered whispers of alien technology, their structure obscured by interstellar static. This isn't just speculation. Researchers at the SETI Institute now model gas cloud interference when scanning exoplanets for artificial signals, recognizing that the medium matters as much as the source. Yet the greatest mystery remains the clouds themselves. Where did they come from? Some theorists propose they're remnants of protoplanetary disks, the birth clouds that once swaddled these infant systems. Others suspect violent collisions, perhaps between planets or moon-sized bodies, could have vaporized enough material to create temporary radio-distorting halos. The most intriguing idea involves evaporating exospheres, where intense stellar radiation slowly strips atmospheres from close-orbiting planets, feeding a permanent haze of free-floating gas around the star. If true, this would mean the radio glitches aren't just noise, they're the dying cries of planets being slowly cooked alive by their own suns. What makes the Kepler radio glitches so compelling is their duality. They're both a nuisance and a gift, a reminder that the universe rarely serves up clean signals, but also a tool for probing environments we can't otherwise see. Every distorted burst encodes information about the hidden structures shaping it, turning what might seem like cosmic static into a Rosetta Stone for decoding alien atmospheres, magnetic fields, and even potential technosignatures. And as newer telescopes like the Square Kilometre Array come online, capable of detecting exoplanetary radio emissions with unprecedented clarity, one thing is certain: The more we listen, the more we'll realize how much the universe enjoys playing tricks with our ears. Exoplanet atmospheres and interstellar gas clouds might seem like separate cosmic phenomena, one wrapped tightly around distant worlds, the other drifting aimlessly between the stars. But when their paths cross, the results can be stranger than fiction. Take the case of HD 189733b, a scorching, hot Jupiter, 63 light-years away, whose atmosphere wasn't just leaking hydrogen. It was being violently stripped away, creating a comet-like tail 70 times longer than the planet itself. Telescopes caught this stream of gas colliding with the interstellar medium, sparking shock waves that emitted bizarre radio static. The planet's atmosphere, once a self-contained shroud, had become entangled with the surrounding void, morphing into a hybrid structure that blurred the line between planetary and interstellar. This interplay isn't just about destruction, it's a two-way street. When NASA Hubble studied the exoplanet WASP-12b, they found its atmosphere bloated with material stolen not just from the planet, but from the interstellar clouds it orbits through. Like a sponge soaking up dye, the planet's gravity was siphoning molecules from nearby gas clouds, weaving foreign elements into its own air. The result: a chemical fingerprint that baffled astronomers. Carbon monoxide levels 10 times higher than expected, mixed with traces of silicon that shouldn't exist in a world so close to its star. The gas clouds, it turned out, weren't just background scenery. They were active participants silently reshaping the planet's very composition. Then there's the mystery of ionospheric bridges. In the TRAPPIST-1 system, 7 Earth-sized planets orbit so tightly that some share atmospheres, their outer layers brushing against one another in a delicate dance. But recent radio observations revealed something unexpected: faint tendrils of ionized gas stretching beyond the planets, connecting them to the surrounding interstellar clouds. These bridges behave like cosmic conductors, funneling charged particles between worlds and the void. During stellar flares, the bridges light up with aberrant radio bursts, their signals distorted by the turbulent gas they traverse. It's as if the planets and the interstellar medium are locked in a constant, invisible dialogue, trading matter and energy in ways that rewrite the rules of planetary science. The most tantalizing cases involve rogue planets, worlds untethered to any star, drifting through interstellar space. Without a host star's light to illuminate them, these nomads are nearly invisible unless their atmospheres collide with dense gas clouds. In 2022, radio telescopes detected millisecond bursts from a region near the Orion Nebula, each pulse carrying spectral signatures of ammonia and water ice. The likely culprit, a rogue ice giant, its frozen atmosphere sublimating as it plowed through a molecular cloud, creating shock waves that lit up the radio spectrum. Here, the gas cloud acted like a celestial spotlight, revealing a world that would otherwise stay hidden in the dark. What makes these interactions so critical is their deception. A signal that looks like a dying star or a chaotic nebula might actually be an exoplanet's atmosphere wrestling with interstellar gas. Until recently, astronomers assumed such distortions were noise to filter out. Now they're mining these anomalies for clues, recognizing that the universe's most intriguing messages often come garbled, not because they're unimportant, but because they're entangled in the cosmic medium's embrace. The next time a strange radio whisper drifts across the void, it might not be a star or a cloud calling, but something in between, a fleeting hybrid of planet and space, singing in a language we're just beginning to understand. At the heart of our galaxy, where stars crowd so thickly they blur into a golden haze, something whispers. Sagittarius A, the supermassive black hole anchoring the Milky Way, isn't just a gravitational monster. It's the source of a faint, repeating radio signal that pulses like a fragile heartbeat beneath the cosmic noise. Unlike the violent flares we typically associate with black holes, this whisper arrives quietly, fluttering between 1300 and 1400 megahertz before vanishing for weeks or months at a time. The pattern isn't random. but decoding its meaning has become one of radio astronomy's greatest challenges, thanks to the swirling storm of gas clouds that shroud our galactic center in an impenetrable veil. These intervening clouds act like layers of frosted glass, each one warping the original signal in subtle ways. By the time Sagittarius A's whisper reaches Earth, it's been stretched, smeared, and scattered by charged particles in the interstellar medium. Imagine trying to hear a friend speak through a hurricane. Their voice isn't just muffled, it's fractured into echoes that arrive out of sync. That's precisely what happens to the black hole's emissions as they traverse the turbulent gas surrounding it. The densest regions, like the 50 light-year-wide central molecular zone, absorb lower frequencies entirely, leaving behind a distorted skeleton of the original transmission. What makes this signal so tantalizing and frustrating is its quasi-periodicity. Unlike pulsars with their metronomic precision, Sagittarius A's whisper follows a loose rhythm, flaring roughly every 76 days before fading into the background. Some researchers believe this could reveal processes at the black hole's event horizon, wherein falling gas creates shockwaves that ripple outward in semi-regular bursts. Supporting this, the Atacama Large Millimeter Array detected clumps of molecular gas spiraling toward the black hole on similar timescales. But here's the catch: those 76 days might be an illusion. Gas clouds along our line of sight could be lensing the signal, creating false periodicities by selectively amplifying certain pulses while suppressing others. The gas doesn't just distort time, it scrambles the signal's very structure. In 2020, a team using the Mir-Kegri telescope discovered something bizarre: the whisper's polarization. The orientation of its radio waves twists dramatically as it passes through the galactic center's magnetic fields. This twisting, known as Faraday rotation, suggests the intervening clouds are far more magnetized than anyone suspected. Instead of being passive filters, they're active participants, imprinting their own signatures onto the black hole's emissions. It's as if Sagittarius is trying to send us a message, but the gas clouds keep rewriting it mid-flight. Efforts to peer through this interstellar static have led to ingenious workarounds. Astronomers now use frequency-agile telescopes to scan the whisper across multiple bands simultaneously, comparing how each frequency distorts to reconstruct the original signal. Machine learning algorithms trained on simulated gas cloud interactions can deblur the data, much like software sharpens a shaky photo. These techniques have revealed tantalizing hints of substructure, tiny fluctuations within the whisper that might trace back to plasma instabilities near the black hole's accretion disk. But without knowing precisely how the gas clouds alter the signal, it's like trying to reconstruct a symphony from echoes in a cavern, the greatest irony. These frustrating gas clouds might also hold the key to understanding the whisper's origins. Recent studies show that certain molecular species, like hydrogen cyanide and methanol, preferentially absorb specific frequencies of the black hole's emissions. By mapping which frequencies get blocked, astronomers can reverse engineer the cloud's chemical makeup and, in turn, deduce what the original signal must have looked like before it was filtered. It's a cosmic version of reading between the lines, where the gaps in the data tell us as much as the data itself. As we listen to Sagittarius A's whisper through the galactic static, we're reminded that in astronomy, the medium is never just empty space. Every signal carries two stories, one about its source and another about the turbulent sea of gas and magnetism it had to cross to reach us. And sometimes the most profound discoveries come not from cleaning up the noise, but from learning to read the noise itself. The next time that faint pulse flickers to life, it might not bring answers, but it will remind us how much there still is to hear in the universe's quietest corners. From the echoing silence of Oumuamua to the rhythmic whispers of Sagittarius A, these 25 unexplained signals paint a portrait of a cosmos far stranger than we imagined. Each one, whether a fleeting burst or a persistent beacon, shares a common thread. the invisible hand of interstellar gas clouds shaping, distorting, and sometimes inventing the messages we detect. These cosmic giants aren't just passive backdrops, they're dynamic storytellers, adding layers of mystery to every transmission that passes through them. The wow signals haunting one-off nature, the Lorimer Burst's explosive power, the eerie precision of the Andromeda transmission. What unites them all is how gas clouds amplify their enigmas, turning cosmic events into riddles that linger for decades. Consider the irony. These same clouds that scramble signals into obscurity also hold the keys to decoding them. Without the Faraday rotation induced by magnetized gas, we'd never have mapped the Milky Way's hidden magnetic fields. Without the scintillation of interstellar plasma, pulsar timing would lack the precision that makes it a universal clock. Even the frustrating distortions in fast radio bursts have become tools, letting astronomers weigh the universe's missing matter by measuring how much these signals slow down as they traverse the cosmic web. The gas clouds giveth as much as they taketh away, revealing secrets in the very act of concealment. What's clear is that our search for cosmic truths is evolving. No longer do we chase pristine signals untouched by their journey through space. Today's astronomers embrace the noise, recognizing that the universe's most profound messages often come wrapped in interference. The next great discovery might not be a clean, repeating beacon. It could be a signal so warped by gas clouds that we initially dismiss it as static, only to realize later that it was the whisper of something extraordinary all along. So keep listening, keep questioning. The night sky is a mosaic of mysteries, and every unexplained signal is an invitation to look deeper. With telescopes like the Square Kilometre Array coming online and AI refining how we sift cosmic noise, we stand on the brink of revelations that could rewrite textbooks. Maybe you'll be the one to spot the next anomaly, the signal that doesn't fit, the pattern that defies explanation. Until then, share your wildest theories in the comments. After all, the universe didn't promise us answers, only endless questions, and the thrilling chase to unravel them.